Hi and welcome to this quick video about compressing images in Python using SVD. So, what's SVD? SVD stands for Singular Value Decomposition. It's a way to divide an image into three components. And as we can see here, A is the original image, and on the right side we have three components which are the end result of using SVD. The first component is U. It's the unitary matrix. The second component is capital sigma. It's the rectangular diagonal matrix of singular values. And the last component is this V, which is also a unitary matrix. So when we run numpy in Python, numpy.svd, we are going to have the result which we see here. We are going to have these three matrices. But how does this actually work? How does this achieve compression for images? Let's see. First, let's see how does this capital sigma matrix looks like. So if we go here, the capital sigma matrix has some elements on its diagonal, but everything else is zero. And these elements on the main diagonal are the singular values for matrix A, for the original matrix. And any SVD algorithm you are going to use is going to return these singular values in an orderly way. So you will have always sigma 1, the top left singular value as the highest singular value. The next one, sigma 2, is going to be smaller than sigma 1, but it's going to be either the same or higher than sigma 3, and so on. So it's already ordered from the highest value to the lowest value. That's important because we are going to use this property of SVD to achieve image compression in Python. And the overall process of SVD looks like this. Let's pretend that we have an image with 26 pixels, and the size of this image is 6 times 4. If that's the case, we can see that we have four singular values, because these four singular values are going to be on the main diagonal of the sigma matrix, here, 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 and here. So SVD output is going to return these three matrices, and the first one is going to be U, 6 by 6. Second one is going to be sigma, capital sigma, 6 by 4. And the last one, V, is going to be 4 by 4. As you can see, if we would multiply this, matrix multiplication, we would have as the end result a matrix with dimensions 6 by 4, right? So this is when we call numpy's SVD method. This is what we are going to get. So these three matrices. Okay. How we can use this to compress an image? We can use this simply by discarding the small values of the small singular values. So we can say that in this example we have total of 4 singular values, but we are going to use only 2 of them, the highest values, the two highest singular values to reconstruct the original image. If we decide to do this, we are going to save some space, because you can see here, in that case, we need only these blue parts of these matrices. So if we are going to use two singular values, we need only this part of U matrix, this part of sigma matrix, and this part of V matrix. As you can see, it's quite a good compression ratio here. But this is just an example, of course. The results we are going to achieve with SVD can vary a lot depending on multiple factors, but the idea of this tutorial, of this example, is to show you how it can be used and how it works. And there are other also image compression methods that are more powerful for image compression than SVD, but SVD is also an option and it works quite nicely. It's not computingly expensive, and it has also many other uses in machine learning and all kinds of computing in today's world. So we are going to see here the image compression, and let's move to example in Python. We are going to need these three libraries or three parts of Python, and these three are going to be NumPy for representing matrices as NumPy arrays. We are going to use SVD function, which is going to perform the actual SVD, and we are going to use the pillow library for image opening and displaying operations. Okay, so let's see the code here. It's quite a short program actually. We are going to use NumPy, and we are not going to use this, and we are not going to use this. We are going to use NumPy and also the pillow image library, and we are going to make two separate functions. One function is going to be open image. It's going to open up an image, this one. This is going to be the test image. And here, when we open it, we are going to decompose it internally into three components, into red, green, and blue channels. And these three channels are going to be used each by SVD function to achieve some sort of compression. After we define open image, we can define compress single channel. So what this function is going to do, it's going to take a matrix for a single channel, for example, a red channel, and then it's going to perform SVD on that channel. As you can see, we are going to use only a specific number of singular values to achieve some compression, and then we are going to multiply u times sigma, but this is, as you can see, this is compressed version of u and compressed version of sigma matrix, because you can see we are using only the first k components. And after that, we are going to convert the result back into unsigned integer, because the original image was also coded as the unsigned integer array. Okay, and our main program does this. It opens up this image we saw earlier. It sets some constraints, like the image width and height are going to be both 512 pixels, and we are going to use 160 singular values, the first 160 singular values out of total of 512, right? So if we decide to do this, we will go channel by channel. We will decompose first channel and compress it. So our function is going to take the original channel data and decompose it. Then we are going to have green channel and blue channel compressed. After that, we are using a helper function to convert from array to a proper image channel in Python in pillow library. We are using the pillow library image dot from array to return from numpy array to pillow image, right, to a single channel. And after this is done, we are going to simply merge the three channels back to the original to to a new image that's going to be the compressed version of the original image, right? After this is completed, we have in original image the original image, and in new image we have the reconstructed compressed image, and we are going to show them both. We are going to first show the original image, then the compressed image. After all of this is done, we will try to calculate the ratio to see how much space we have saved in this operation, right? So let's run the program and see how it goes. This. Okay, so on the right side, we can see the compressed image. On left side, we can see the original image, right? So here they are. We can use some scaling here. And you can see the quality is not that bad on the right picture. And let's see about the compression ratio. It says that compressed image size is 62% of the original image size. So we have, let's say, a nice compression ratio. It's nothing spectacular, but it's nice. Let's see what it's going to be if we decide to use a smaller set of singular values. So let's say if we decide to use only 100 of them. Okay, now you can see the image quality starts to show as it starts to be a problem, because you can see that we have some rough edges here and it's not that good. So, but the compression ratio is much better now. We are using only 39% of the original size, right? One more test. Let's see what's going to be if we decide to use only 25 single values. Okay, this is now a drastic reduction in quality, and it's almost unusable, but the compression ratio is great. We are using only 9 or 10% of the original image. So let's say we are going to use the original 160 values, and to see the result, here it is. Yeah, it's not perfect, but it's not that bad, right? Okay, so here it is. Here is how we can use SVD and NumPy in Python to compress an image, uh, and how we can display the result and everything. And if you want this source code, just please send me a message or post a comment. I will be happy to send it over to you. This is for educational purposes only. This is nothing production ready. This is nothing you are going to use like a final solution for any kind of serious compression. But it's quite a nice example, I guess, of how we can use SVD to reduce the space we need to store an image. In a similar way, SVD could be used to save space or to make predictions in other parts of computer science, but that's a topic for another time. Thank you very much and have a great day.